In this video we will discuss scheme forms, special forms and lambda expressions. So let us start with this form. It consists of 3 parts and it is parenthesized. The basic evaluation rules in scheme is that each of the 3 constituents of the form is evaluated in the same way. So A is evaluated, B is evaluated, and C is evaluated. And in order to apply this form, it must be the case that the value of A is a function. And this function is then applied on 2 parameters, namely the value of B and the value of C. So that's a basic rule. But there's special rules, namely in the case where A names a special form. And let's take a look at a couple of examples of special forms. And the first special form is the case where A is the name defined. So the first constituent of our form is defined. And in that case, special rules apply. And the special rule is here that B will be bound to the value of 5 at top level. So the second constituent B is not evaluated, but the third constituent, which happens to be 5 here, is evaluated. Another example of a special form is if, which is conditional evaluation, and here we first evaluate the second constituent, and in case that evaluates to true, the third form is evaluated, else the fourth form is evaluated. So that's conditional evaluation. Either we evaluate the third form or the fourth form of an if. The final special form we will bring up here is the lambda expression. And so here we can see the first constituent names a special form, corresponds to A. It is lambda, and therefore there is a special evaluation rule. This expression evaluates to a function object, a function of 2 parameters where the body is this expression. Let us return to our first form A, B and C, and it does still not succeed. So in order for us to make this a success, we should bind A, B and C to values, and the value of A must be a function. So we can define A to some function. Now A is defined by means of a defined form. And what is the value of A? The function that adds the squares of its parameter. Just like before. Now A has a value and it is a function. B has a value because B got the value 5. So now the only thing missing is that C must have a value. C is still undefined. So we could define C to a value. And now this form evaluation will be successful because A evaluates to a function object, B is defined to 5, and C is defined to 7. And now we get the expected result. It is possible to redefine names in scheme. So in case we do not like the bindings of A, B and C, we can redefine them. So with A, it is possible to redefine A to another function, namely the function that subtracts the squares of x and y. in this way. So now A subtracts instead of adds. And we can also redefine B to be, for example, 6 instead of 5. You may now ask if redefinition is equivalent to assignment, and it is not. And let us show why it is the case. Let's take a look at this special form where we try to program with define. So in case A is a procedure, in case A is a function, we will define B to 7, else we will define B to 8. This is not legal. You can see we get an error. So if you really want to do this, we must use assignment. It is the special form, set exclamation mark, but assignment is not part of functional programming, so we do not use it. We now take a closer look at lambda expressions. Here we have a lambda expression with two parameters A and B. But what is interesting is that in the body of our function, there are three names F, G, and C, which are unbound. So they rely on the context. And there are many possible contexts. Here we have one possible context where we see bindings of F, G, and C. So F is bound here, G is bound here, and C is bound to the first parameter of the outer lambda expressions. So the important thing here is that we have established bindings of the three names in this lambda expression. Now it may be the case that our lambda expression is returned from the outer level such that we end up in a situation where we have our lambda expression outside the context where F, G, and C are defined. And the point is that this context cannot be deleted. It must exist because there are bindings of F, G, and C in our function object which relies on the meaning of F, G, and C. Let us take a concrete and practical example of this phenomena. We define a function which we call makeComposer. That's a function which takes a single parameter, func. So this is the binding of func, and the body of this function returns the value of our lambda expression which depend on func. So let's call makeComposer with the plus function, the addition function, as our parameter. So this will return the value of this expression, which is a function. So let's do it. Let's bind this value to F. So makeComposer, still applied to F, is now bound to F. So what is F? Well, this is again some function. This is the value of this lambda expression. Now we can apply F. It takes two parameters, and these two parameters could, for example, be 1 and 2. So we get the value 3. The value of a lambda expression is a function, but we also call it a closure. And the reason is that a function object depends on bindings of the three names, the red names here. So the binding of F and the binding of D and the binding of C are necessary in order for us to work with this function object. We have seen this form of function definition. Using the special form define, a becomes the value of this lambda expression, a becomes a function. There is, however, an alternative syntax for function definition which I use very often. And this is a special form of define, namely in the case where the second element of the define form is a list. Here the second form of define is simply a name, but if it is a list, the lambda expression here is implicitly defined. This form and this form is exactly the same in scheme, but this is often slightly more convenient because two things. First, we have the calling form of our function here, which is convenient, and as you can see, there is one layer of parentheses less in our convenient form than in our basic form of function definition. So therefore, it is often attractive to use this abbreviated form for function definition, where the lambda of our function is implicit.